All right, welcome everybody. So this is chapter 19, chapter on reinforcement learning. And we've talked about supervised learning. We talked about some generative models and other models that are semi-supervised, unsupervised. And there's one chapter here now to talk about reinforcement learning. Reinforcement learning is a huge sub area in machine learning. It's really hard to do it justice in one chapter. So we'll go through many of the concepts that are being reviewed here. And I thought that this chapter had the math, but it was a little bit light on motivation. So I am not a super expert on reinforcement learning, but I think there's a few key points that I'll try to sprinkle in terms of like, okay, we're going to list like 6, 7 techniques, but like why? Like why don't we just have one of them? Like why do we need these other ones, right? But feel free to ask questions. You can unmute or you can put them in the chat. So I'm going to go through the chapter contents of the book instead of using slides today, and I think we'll just kind of go through the different concepts as the author explains, and then if necessary, we can try to pull in some other resources. Okay, so what is reinforcement learning? Reinforcement is this framework, and basically the way it works is you have a single scalar signal. So you can have a 1, a 0, you can have fractional values, you can have negative values. And the goal is that you basically have an agent in an environment over time, and it's trying to maximize its rewards. And of course, as with like sort of any kind of life decision over time, the short-term biggest gain is not always equal to the long-term biggest gain. Okay, and so trying to maximize the long-term is really complicated. And thus you need some strong tools. So to start this off, basically we're going to start off talking about a bunch of terminology. And so there's terminology like Markov decision processes and returns and all of this kind of stuff. And so we want to kind of walk through all of this so we have some common language to talk about how we're going to attack this problem. Okay, so starting in this section 1, let's talk about processes. So first, we're going to talk about Markov process. This will be a first order Markov process. And the idea here is that you have some state, and you can represent the state any way that you want. And essentially, the key property is that you don't need to know anything about the history. That all of the dynamics of the system depend only on what state you're in. Okay, so I watch baseball, and if you said the state is how many balls and strikes to the current batter, that's not enough. If you said it's how many balls and strikes and what runners are on base, that's still not enough. You also need to know like what inning, how far into the game you are, and what the score is. But if you combine all of those things, then yes, you don't really need to know exactly how things happened earlier. You just know that, hey, this team has 2 and the other team has 0. And so this is like sort of the current state of things. That's a little bit of an oversimplification. But so once you know that something, or once you've modeled something as a Markov process, then that's going to simplify a bunch of the math because you're just going to refer to what your current state is. You don't need ginormous amounts of history. So we can then expand on this a little bit, and instead of a Markov process, we can now talk about a Markov reward process, where every time you transition from state 1, from a certain state at time 1 to the state at time 2, then you're given this scalar reward. And it could be 0, it could be a big number, it could be negative. So ultimately, as you go through time, you're going to pile up these rewards. And again, what we're going to try to do is we're going to try to maximize them. If you do the math on this, and you're talking about doing this infinitely, forever in time, usually there's like ending conditions, but if you do this like infinitely over time, then you have a problem that the sum of these rewards could be infinite. Okay, and so the way these are modeled is with this discount factor, and the standard letter that we use to represent this is the Greek letter gamma. All right, and if gamma is a number less than 1, it's between 0 and 1, then basically, you know, if you're familiar with like geometric series and stuff, so this causes things to converge. It also often models realistic situations. So if I said to you, I will either give you $1 right now, or I'll give you $1.01 10 years from now. You know, like, yeah, it's a penny more, but you would just say like, but that's so far in the future, I'll just take the $1 now, right? Whereas if I said, I'll give you $1 now, or I'll give you $100 next week, well, because that's not that far off, the discount's not that much, it's still going to be worth more than $1, right? So in many situations, this is a realistic thing. And, you know, in economics, you talk about time value of money. So this is a pretty common concept, but it is needed in these proofs in order to make sure that all of these things converge, or otherwise you could have infinite rewards, and then it makes it just much more difficult to manage things. So those are both of the reasons why we want this discount factor. We have a bunch of figures. I'm not necessarily going to spend too much time, but it is helpful to sometimes just look at a small toy problem if you're having trouble understanding some of these concepts in RM. So here's this diagram that pretty much anytime you do introduction to reinforcement learning, you see some version of this diagram. Okay. And the idea is that there is this environment. You may not have control over this environment, but there always is some environment in which your process is happening. It could be a game like chess. It could be a self-driving car driving on roads, but there's some sort of environment. And you have to encapsulate everything that you need to know about the environment into a state. And this is going to be what we'll talk about. One of the problems that we're going to run into is the size of this state space could be just absolutely ginormous. And so realistically, it may not be tractable for you to do so, but at least conceptually, you have some state that tells you about the current. And then what we're going to talk about is, we've already talked about this reward. So every time you do a transition, there's a reward. But then one of the other things we're going to talk about is that if you're doing RL from the perspective of the agent, then the agent is going to decide on actions that it takes. So you could model certain processes where basically like you have no control, just random things happen to you. You're just like a molecule bouncing around in a box, you know. But most of the time we're talking about things like processes that we're trying to optimize our choices. And so if it's chess, if it's poker, then you know you're deciding what move should I make. And so after you decide what move to make, then based on the environment, you wind up in a new state at the next time step. And so then this process just repeats. So you'll see some version of this diagram in every RL introduction. So we were talking about Markov processes, and so now we're going to get to Markov decision process, and this is where I was talking about, where now we have a set of actions that we can take at each time step. And you can have a very fixed action, a very deterministic policy, or you can have a stochastic policy where you have a fixed probability distribution, but you sample from that. So you could say, a third of the time, I'm going to take a step to my left, and 2/3 of the time, I'm going to take a step to my right. And that's a very fixed distribution. But if you were to do this same thing over and over again, you're not always going to take the same action. Sometimes you're going to go left, sometimes you're going to go right. So if you write this out in terms of what happens, then you'll sort of see that there is a state for a certain time step, and you choose your action for that one. And then you get a reward, and then you wind up in a new state, and then you repeat all this where you take an action, you get a reward, you wind up in the next state. There's some details of the bookkeeping, whether you call this like R sub 1 or R sub 2 or whatever, and I sometimes get a little tripped up on that. But it's like in terms of just the bookkeeping, you can see it makes sense. State, choose your action, get a reward, then you wind up in your next state. There's a note here. We're not going to talk about it too much, but if you think about I don't know. There's toy problems where basically you have a fully observable environment, maybe like Pac-Man or something like that, where you can see everything. But there are a lot of situations where you don't know everything. So, for example, in poker, you don't actually know what cards your opponents have, so you do not have access to the full state. And so there's a technical term for this as well, which is partially observable. So partially observable Markov decision process means you don't know everything. And we do need another letter to differentiate the parts of the state that exist in general versus the parts of the state that you actually are able to see. And so that's your observations. So then if you're writing this out instead of SAR, 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 now you have SO, AR, SO, AR, so on and so on. All right, so the next piece of terminology is policy. And so if you just write down all the rules for what you're going to do in a given state, then that's your policy. Again, your policy could be deterministic, 100% when you're in this state, do that. Or your policy could be stochastic, saying do a random number, flip a coin, and decide whether you're going to do this or that with these probabilities. So the standard letter that's used to denote the policy is the Greek letter pi. Okay, and then using more formal probability terminology, you can say, you know, our policy is the probability that we take action A given that we're in a certain state S. There's also this idea, mostly we're going to talk about stationary policies because we're trying to model this as a Markov decision process. But theoretically, you can also talk about non-stationary policies where over time you change your policy in a pre-planned way. Theoretically, you could sort of bake that time factor into your state and then it becomes stationary, but at least conceptually, it's like, yeah, when I start out, I'm going to do whatever, and then over time, I'm going to start to, you know, and so like, you know, you might like explore more early on, and then explore less later on, for example. Okay, so that's a bunch of like introductory terminology just to kind of set things up, so so we have some language to talk about modeling these things. Any questions so far? Just boom, jumping into all the terminology. Okay, so let's talk about the next section. So now we're going to get into some other concepts. So the idea of returns. So we said that we're modeling this as a reward, but what we really care about is the reward over time. Let's actually get some more terminology around this. Okay. And so in this case, the return is the sum of all of those rewards. So the reward is a single time step reward, and the return is from now until infinity, from now until this process ends. We need a letter for that, and traditionally the letter used for this is capital G. I don't know why capital G, but you'll just see this in most books and most papers. And so if you were, say, playing chess and you assign different rewards for different steps throughout the game, it could be as simple as all the rewards are 0, and then at the end of the game, you get a +1 for winning and you get a -1 for losing, or you could have incremental values in between. Okay. What we really care about is not so much what was your return in a given game. What we really care about is what is the expected value of your return. So if I make this as my very first opening move in the chess game, what I really want to know is, right, what are my odds? How does that affect the way the rest of this game is going to go. And I'd prefer a move that has a higher reward, higher return on average than one that has a lower return. So when we're talking about a particular game, a particular episode sequence of events, then we're going to talk about a single G. But what we really mostly care about is the expected value. And so the expected value for this has a letter, and it's lowercase v. So this v is actually a super important concept in reinforcement learning. And so the actual v is whatever the expected value of that action, that move is. Generally speaking, this is not known. Okay, this is something we'd like to know. So we might estimate v, but the true v is usually not known. This is sufficient information for you to decide like what's due and everything, but generally speaking, it's not that convenient because the environment controls what state you wind up in. So you can control your actions that you take, but you can't directly, depending on the environment, you don't as directly control what state you're going to wind up in. So it's a little bit easier to talk about if I'm in this state and I take this action, what is the expected return from that? Okay, so what we see is that instead of working with v, almost all the time we end up working with this function q, which is a much bigger space. So instead of having one value for every state, we have one value for every state action pair. Okay. And so under a given policy, given set of choices, what is the expected value from this? And again, we typically do not know the true value of this Q function. It's something that we are estimating in order to figure out the best actions. And intuitively, you can imagine that if you're in state 11 and you have 4 different actions you can choose from, and you knew Q, you would just choose the action that has the biggest Q. I mean, right? This is not the short-term return. This is the long-term average reward. Sorry, not the short-term reward. This is the average long-term return you're going to get. Just pick the one that's the biggest. Okay. So conceptually, that makes sense. The problem is, like I said, we don't know Q. Okay. For like a very simple game like tic-tac-toe, you can calculate all this out. But for all the realistic situations where we want to apply reinforcement learning, it's not something that we have at hand. Okay, a little bit of notation. So if we're going to choose the best actions, we're going to maximize these, then the notation we use is star. And so sometimes it's a superscript, sometimes it's a subscript, but you see V star is telling you what is the maximum value that you can get from each state. Q star is the maximum return that you can get for each state in each action. And so then ultimately, if our policy pi is what choices do we take in every state, then you can imagine that you just do this argmax. You just say, I'm going to, what I was saying earlier, I'm just going to pick whichever action for a given state is the largest, then that's the one that I'm going to pick. All right, let me pause here with, like, again, a bunch of terminology that I've thrown at you guys. Any questions so far? All right. So then the next thing which I'm not going to go into too deep, but if you have these notions of a V function, a Q function, a policy pi, and there are optimals, whether we know them or not, we can actually say that there are some properties of these different functions and how they relate to each other. And so we get into these equations that Bellman, I'm blanking on his first name, but in reinforcement learning, the Bellman equations are very famous and they're very fundamental. Okay, so for the value of a given state, you can just simply say, I'm going to sort of sum up the value from all of the different actions that I could take at this given state. That makes sense. So if you have 4 actions you could take, if you just sort of sum up each of the returns for each of those 4 actions, along with the probability that you choose them, now you know what the value of that particular state is under your policy. The other thing is with your definition of the return and reward, what we're saying is we apply this gamma multiplier times future rewards. And so you can then say that my value at a given state is the reward I get right away plus gamma times everything that I do in the future. All right. I'm not going to go super deep into the math here, but you can keep going with these sort of just like expanding things out and looking at the relationship between Q and V. And eventually you can get to like these equations 19.9 and 19.10. And one of the things that we can do is instead of having a relationship between V and Q, okay, if we keep expanding things out, I can get it to the point where I can express the relationship of my value V for a given state to the value V of the state one time step later. So now instead of needing to have 2 functions, and instead of needing to have V and Q, I have a function that is just dependent on V. And of course, it depends on what my policy, what actions I choose to take, and it depends on the rewards that the system gives me. But so this somewhat recursive formulation is far more convenient. And you can imagine where we're kind of going to in the next section is that if I thought that the value here was very low, okay, but it turns out that the next step I'm going to get a huge a return. I'm going to get 100, and then whatever the discount factor is 0.9, that's still like 90. So if I knew that in the next time step I was going to get back 90, then my estimate of the current value being 0 would be very inappropriate. And so what I probably want to do is bump up my current estimate to something like 90. You can do the same thing with the Q function with states and actions. And so again, it takes a bunch of plugging in, spending things out. But if you look on the right, what you'll see is all you have is the Q at a certain time step, dependent on the Q, the next time step, and then of course your policy, what actions you take in the environment giving you rewards. So similarly, if I take this action and I think that the return for this is going to be very low, it's going to be 0, but it turns out once I get to the next state and I take an action, I'm going to get back 100, discounted by a factor of 0.9. If I'm going to get back 90 one step from now, then estimating that the total return is 0 is going to be very, very inaccurate. And so we're going to use these relationships in 19.9 and 19.10 fundamentally in order to try to correct any estimates we have, say for the Q function. So if I had a previous estimate here, I can go one step forward, I can go many steps forward, and I can compare the returns that I'm getting, the rewards that I'm getting to what I was expecting. And based on that, I can then update my estimates. That's the core of where we're going. So the simplest place to start is with what we call tabular reinforcement learning. So the idea here is we talk about states. What if you had a small enough number of states that you could just write it out? You could write it out on paper. You could record it in computer memory. So tic-tac-toe, whatever. There's only whatever hundreds of states or whatever. It's a relatively manageable number, and so you could actually literally just create a table on your computer, and you could have all of your states, and you could have estimates for either your V or your Q function, and just write things out that way. So we'll talk about a couple techniques where we don't yet need neural networks. We don't yet need super complex things in order to make all of this tractable. Okay. So the first concept is dynamic programming. Dynamic programming is discussed in places other than reinforcement learning in computer science and mathematics. And the basic idea is if you had perfect knowledge, this is the key thing right here. If you had perfect knowledge of the environment and how it works, and then you would know with 100% certainty, if I take this action, then this is exactly the probabilities of what new state I'm going to wind up in and exactly what the rewards are. So my guess is that like Atari video games fall into this category, that it's programmed a certain way, and you know that if you do this and you shoot that thing, then you're going to get this many points. And if you do that, then you're going to whatever, right? So you know exactly the rules of this. There is some randomness, you know, it may be that the thing you're trying to shoot might have a 50% chance of moving left and a 50% chance of moving right, but those dynamics are fixed. So if you have this perfect knowledge, then basically what you can do is you can just make a ginormous tree of all the possibilities of what could happen. Okay. And you can figure out the value, the return that you get at every branch. That's one thing you can do if it's like really small. Okay. But to write out the whole tree, even like for tic-tac-toe, I think that would be somewhat tedious, let alone a game like chess or Go or backgammon. So what you can do that's like a little bit better than that is you can do this two-step process for dynamic programming, where you do what's called policy evaluation and policy improvement in alternating fashion. So policy evaluation says that I have a policy that I'm going to take these actions in these states. And all we're going to do is use our value function to recalculate what the long-term returns are. So like I was saying, if I currently think the value is 0, but I'm going to get 100 in the next step, then I'm going to update my value to be 90. Okay. Policy improvement says I'm now going to do an argmax. With all my updated values, I'm going to actually choose, I'm going to pick the one that has the highest long-term return. And if you do this iteratively and you alternate, then eventually this is guaranteed to converge for finite processes. And so we kind of start our discussion with dynamic programming. Dynamic programming is a good example of like working with these equations, but there are no real life situations where you have perfect knowledge of the dynamics of the system. So it's not really a practical thing. It's more of like a textbook exercise to get your juices flowing, understanding the equations. So the first realistic thing that we can talk about is Monte Carlo methods. And so basically, imagine that you're doing, I don't know if tic-tac-toe is a great example, but you're doing tic-tac-toe and you say, what if my first move is I put an X in the upper left corner? Well, a simple thing you could do is you could play 1,000 games of tic-tac-toe and you can see what is your rate of winning and losing time. And then you could say, well, what if I put my X in the whatever top middle and play 1,000 games and see what your average is? Okay, that's essentially what Monte Carlo methods. So there's Monte Carlo is a term that's used a lot in a lot of different areas. So we're talking about this very specific thing in RL they call Monte Carlo methods. So the new terminology we're going to introduce here is the idea of an episode. So most realistic things we do have an ending condition. So in this case, tic-tac-toe, the game is going to end when someone wins or else you filled up all 9 boxes. Okay, so it doesn't go on infinitely. So you can do just a bunch of episodes and then you can see how you did. Monte Carlo methods basically have like the strong mathematical foundations that say um, um, this will in the long run this will converge, and this will tell you the probability of all of your states or all of your actions or whatever. So we're done, right? So one of the things that I thought was again a little bit light in this chapter is it doesn't talk about motivation. So the problem with these Monte Carlo methods isn't that they don't work. The problem is the sample efficiency. Okay. For tic-tac-toe, maybe you could play 1,000 games with different starting positions and you could, whatever. And then if you like starting with putting the X in the upper left corner, then you could do 1,000 games for your second move, right? Or whatever, just keep going like that. But even for tic-tac-toe, if you and your opponent each have a total of like 9 moves you can make up to, and you do 1,000 runs for each one of those, then are we? I don't know. So then we're talking about I don't know. You get to a very large number of trials that you need to do for each of the different moves, and then there's like 9 factorial different moves, combinations of moves, right? Times 1,000. So 9 factorial times 1,000 is already a pretty big number, and we're just talking about tic-tac-toe. We're not talking about chess. Okay. So the problem with Monte Carlo isn't that it doesn't work. This is really the fundamental problem with all of reinforcement learning. We have these things, many of which mathematically have been proved will converge. The problem is that if they converge at like 10 to the 2,000th power times the heat death of the universe, it does you no good. You need something that you can run on a computer and like in, some reasonable amount of time, depending on how important the problem is, in, a few days of computer, whatever, you can actually come up with, if not the absolute optimal policy, at least a very, very close approximation, a very good policy. So everything else we're going to see here is about resolving this problem that we have a technical solution, but what we need is one that converges very quickly, that is very practical. So the next thing we talk about is temporal difference, TD learning, okay? And the idea here is that when you do full Monte Carlo, what I talked about is you play out the game of tic-tac-toe. Okay, so imagine you're doing this for chess. You play out an entire chess game, which could be whatever, 75 moves, and then you get 1 point, and you got to do this thousands of times to even get like any kind of estimate. So what your basic TD learning does is it says, let's not wait so long. Let's actually update our estimates after every single move. So you can look at the equations and everything, but essentially, basically, what it's saying is just that we're going to what I was talking about before. We have a certain estimate for what the value of this is, and then if I'm very, very off, if I'm thinking the value is 0, but then I do a move and then I get 90, well, then I should really update my value. In this case, what we're going to do is we're going to have a learning rate. So this is a lot like, if you guys are used to gradient descent, we're going to have a learning rate. We're saying, well, just because I got 90 this time, I'm not going to bump up my new estimate all the way to 90 because maybe I just lucked out, So I'm going to have some alpha factor. That's my learning rate. So maybe this is 0.1, maybe this is 0.01, whatever. And I'm going to bump this up slightly. And so over time, if I keep going through here and I keep getting 90s, then eventually my new value is going to, approach 90, but it's going to take multiple iterations. So just because there's potential noise, there's potential stochastic, aspects to this, we're not just going to immediately plug in the full thing. And so this is a way of updating our Q function. And so there's this term you'll see in reinforcement learning, they call it Q learning. And what people have found, and there's some math behind it that's now been proved, is that you will converge much faster if you update after every time step instead of updating at the end of each episode, waiting until the very end. Um, it might be a little bit like not obvious because these individual updates are very noisy. They have high variance. Like you don't know that just because you got a good return a good reward one step from now that for sure means that your estimate was wrong. But I don't know all the math, but basically it's been demonstrated and empirically people who try TD learning, it just works so much better, converges so much faster than Monte Carlo. Okay. So this is great. This is like a big advancement. I think the next section, um, yeah. So now we talk about fitted TD learning, and so instead of having to have enough memory to list every single state, or in the case of a Q function, state times action combination, what we can do is we can have a neural network, and we say the neural network, you pass in the state and you pass in the action, and it's going to return what it thinks the Q value is. Okay, so we're used to doing this. We build neural networks to estimate things. In this case, we're approximating our Q function with a neural network, and then that allows us to use this temporal difference TD learning on problems that have much bigger states, because if the state is 10 to the 20th power, you don't have a lot of computers that you can like fit all those states into a actual Q table, right? But you can have a neural network that easily will get in its inputs and it'll output values. And so its job is to learn the patterns and learn, where to have low values, high values, and where things with similar inputs are going to have similar outputs, and where it needs to actually, output different things. So without kind of going through the gory details, basically now, just like everything else, we can run gradient descent to say like, hey, let's actually update our neural network in order to have it estimate better Q values. And so what we then see is that where this was demonstrated, one of the big, so question in the chat, does this assume we have an optimal rewards model? So we're going to get rewards from our environment, and so those rewards are accurate. We don't necessarily need to know what those rewards will be. So you can actually start Q learning either tabular for small problems or with a neural network, deep Q learning. You can actually start it with Q values that are just all zero, which is not a very good estimate at all. And they will, over time, update, and they will actually converge to the accurate values. So one comment about this is that a lot of early reinforcement learning success is on problems that you're able to simulate. So like Atari games, fortunately, if you get like the source code or whatever, they're very easy to simulate. And so what this means is if you have a fast computer, you can actually play thousands of Atari games very quickly, versus if it was some other thing like a robot or whatever, and you have to actually literally drive around and in order to simulate it, then to do like 1,000 runs would take you much, much longer than if you can just like simulate it on a fast computer. So technically speaking, RL does not require a simulated environment in order to work, but it just works really well when you do have a simulated environment. And so I bring this up because then your simulated environment has to have accurate rewards that correspond to whatever the problem is that you're really trying to solve. So if you're simulating a self-driving car, your simulator better be fairly realistic, or otherwise you're going to learn how to drive in that environment, which doesn't actually match the real world. So depending on whether you're talking about having accurate knowledge of the rewards, no, you don't need to know anything up front. But if you are doing simulation, your simulation needs to be good. The other question is like, phi, are these the neural network parameters? Yes. And so we are going to use gradient descent. We're going to update these. And if you look here, basically your loss function is just what's the difference between the Q that my neural network estimated and the Q that I'm actually seeing from taking one step. So my previous estimate plus the discounted reward that I'm getting. So that's the general gist there. All right. So Q learning, one of the hallmark watershed moments was basically when people were able to use deep Q learning in order to play Atari games, and they learned to play these games just from the pixels on the screen. So they didn't tell the computer anything about the rules of the game. All they told it basically is that you have a joystick. I guess there's like 8 directions you can move, and you can either press the button or not press the button. All right. And so this was very, compared to a human, very sample inefficient. I think later in the chapter it says something like for each Atari game, they simulated what would have been the equivalent of 42 days of nonstop playing that one game before it would learn anything. But prior to this, nobody had even come close to being able to learn something like that. So if you count up the number of pixels on the screen, it's whatever, I think 320 by 240 or whatever. Whatever that math works out, it's a pretty large number of states. And then if you multiply that by like 16 possible actions for every state, because there's like 128 pixel color values for each state, and it's tens of thousands. It's a big enough number that you really didn't want to have to build out that full table. So instead, they used a neural network, and in this case, I don't think they even used a neural network to represent all of those states. What they did is they took a CNN and they embedded the screen into a smaller space, and then they used the neural network to estimate the Q values for that particular space. But so this was like real proof that you could teach a computer to do something non-trivial. You know, if you have a little toy board that's 5 by 5, and oh look, we taught the computer to do this. It's like, yeah, but a 5-year-old kid could look at this problem and in like 30 seconds figure out what the optimal policy is. So this isn't exactly, you know, knocking people's socks off. But this was good, and in some cases, there were Atari games where you go a long time without any feedback. You know, you're wandering around for a long time, and in some cases, I think their model failed to really learn how to play the game. But for games like Breakout shown here, Space Invaders, whatever, where you have points and the points go up fairly frequently, the computer actually got to the point where it had superhuman performance. It could get a better score than a regular good human. I don't know if they got a better score than like the best person's ever high score, you know, at that point, but it was like at that level. So it was pretty cool that the first time you saw a computer having superhuman performance at something using reinforcement learning. So that's this section, 1941, talking about deep Q networks playing Atari games. So we've got a couple sections here that are now going to talk about, so we figured out TD learning works better, so now we're done, right? And again, this is the same problem. It's like, well, it did work. They got it to work on these Atari games, but then when you tried it on bigger things, it still was so sample inefficient that it might be the case that mathematically it'll work, but it'll take you 10 to the 15,000 years before you'll actually get you know, a model that knows how to play chess or something like that. So one of the problems that they have is this process where you estimate what your value is, and then you're going to actually choose actions So this is considered an on-policy process, where basically you're only getting feedback from the actions that you actually think are the best actions. There's this bias that happens by virtue of you taking the maximum action that you know of. So even if you're wrong and you think that the value is higher than it should be, than it actually is, you don't know that it's wrong, but it's going to cause you to keep taking those actions. And so what this does is this ultimately causes your Q function to perpetually have this overestimating of what the real values are. You have this distinct bias. And so people figured out that a very simple thing you can do is if you had two Q functions and you used one to pick the action and you use the other to estimate the value, now you don't have this problem of this correlation and this bias. And there's different ways that you can do that, but essentially having some doubling of it got people more accurate values. The more accurate values, in general, the faster, the better it converges. So that's a pretty notable thing. If you read the literature, double Q learning, DQN, is something that's like a pretty famous improvement on the algorithm. All right. So with that, with some other tricks, now we can pretty much solve any problem that we want, right? Well, unfortunately, no, because like if you're in the world of robotics, we don't have discrete states like we do in chess or tic-tac-toe. We're dealing with continuous things. So like, one of the simplest problems in the used to be OpenAI Gym, but now it's no longer OpenAI. It's just Gymnasium. But one of the simplest problems you can do is cart pull. Okay, so you have this cart and it's like, imagine it on like train tracks or whatever. It can only move left or it can only move right. And you've got this pole that's on an axle there that's just pointing straight up. And as soon as it gets slightly off center, it's just going to tip over and it's going to fall down. And but what you can do is you can move the cart a little bit left, a little bit right, and you can try to balance the pole as long as you can. It's like if you've ever had like a pencil on your finger and you're trying to keep the pencil from falling down, right? So this only has, I think, 4 inputs. It's like the location of the cart, the speed of the cart, the angle of the stick, the pole, and the speed at which the pole is moving if it's already started to fall. And then you have one output, which is basically like push the cart. How hard do you want to push the cart to the left, or how hard do you want to push the cart to the right to try to fix things? I don't think you can solve this with TD learning. I mean, you can do things where basically you divide up these 4 inputs into buckets, so you discretize it, right? So if you say the velocity under most real world circumstances is between whatever, -10 and +10, so maybe I'll just create 100 buckets and I don't know, maybe that's doable. But generally speaking, if you just naively try to solve this, and this is like a really super easy problem, if you try to solve this with TD learning, generally it doesn't work. So what you'll see is pretty much all of the more advanced modern reinforcement learning uses something called policy gradient methods. Famously, RLHF that OpenAI used in order to fine-tune its ChatGPT models, it is using a policy gradient method. Okay. So how do policy gradients differ from what we've been talking about? We've been talking about really modeling functions of how much reward and return we're going to get based on the states and the actions. Okay. You can do a model-free estimate based just on the policy. So in other words, you're sort of amortizing over time, over the different states from based on what your policy is. And so you can imagine for the cart pole thing, right? You have different situations which you say, oh, I better nudge it to the left because the thing starting to fall down. But how much do you nudge it? That's really the decision you need to make. That's the policy that we're trying to optimize. And what this chapter does is it goes through a little bit of the math to show you how then you can take a look at the states and actions. You can sort of write them all out. And then eventually, if what you do is you try to get the derivative, the gradient, for the parameters theta of your policy. So if your policy is parameterized by some neural network or whatever, and so if you go through, you see there's this thing that comes out that you get this function that basically says the probability of choosing a particular action times the reward that I get from that action. And I think it's written out. Not sure, but if you look at these various functions, essentially, you see here's this update I'm going to do to my policy, where again, here's my alpha learning rate. I'm going to take my old values and I'm going to bump them a little bit by a learning rate of alpha, and what's in this inside the summation, right? What you see here is some version of the probability of me choosing this action times the reward that I got. Okay, so ultimately what it boils down to is something that's fairly intuitive. All right, if you do something and you get a good reward, pump up the likelihood that you take that action. Like gradient descent, just do a slight, bump up. And if you get a very poor reward, then bump down the probability that you're going to do. That's essentially what's at the core of the math behind these policy gradients. But this allows you to work in continuous space, not in discrete space. And so a very, very simplistic policy gradient algorithm. I don't even think you need a neural network. You can just have, I think, just like a linear single parameter or whatever. It will actually do cart pole, and it'll. I don't think it'll necessarily be able to keep it forever, but I think with just like one parameter, you can actually get it to learn to the point where it can keep the pole up for a while. So this is the core of policy gradients. There's this reinforced algorithm, and again, you're going to see that this same structure of the probability that you choose something times the reward, and there's this log in front of it, and so basically, when your probability is close to 1, the log of 1 is close to 0. All right, and what this is doing is saying that if I get a high reward and I'm already super likely to do it, I don't need to update my policy because my policy already says do this. Okay, and so your biggest updates here are going to be when you had something that you originally thought was extremely unlikely, but it had a super positive reward. That's when you say, whoa, wait a second, my policy is way off. As I said, only do this with a 1% likelihood, but this ended up being way better than the thing that I'm doing 99% of the time. And so that's the way that these policy gradients work. There's some tricks again to this, and it gets very, very mathy. I don't understand all the math, but one of the things you can talk about is baselines, and this has to do with the again, we want this to converge quickly. There can be a lot of variance in these rewards that you're getting. So they say you can subtract a baseline value B from your reward. And if the B is completely uncorrelated, then this does not change your variance, right? You've just basically changed the mean. You subtracted a value. But what you can do is to use different values of B in a way that's correlated such that it lowers the variance. And the less the variance, the faster you converge. And so one of the things that they get to is, I said in every section, yeah. So in section 5.4, they say, hey, let's have the baseline depend on the current state that we're in. And so now we're basically saying, let's say this baseline is the average amongst all actions, and we're looking at the reward for a particular action. Then really what you're saying is, how much better is this action than all the other actions on average? All right. And there's a special term for how much better than the other actions, and that's the word advantage. So if you look at a lot of the cutting edge papers in RL, you will see the word advantage quite often, because the goal here is to get your model to converge quickly. And what people have found is that you can reduce the variance, and you can get them to converge much, much more quickly by using this advantage technique versus just using a vanilla reward. And that's really like, again, I feel like there's not a lot of motivation discussed, but really that's what's at the core of RL today. We have the math that proves these methods will converge given infinite time. We need techniques that don't require infinite time to get close. We need techniques that converge very quickly. Yeah, so question in the chat, why didn't RL skyrocket? So even though like Go is a very difficult game, AlphaGo, it still turns out that Go is many, many times smaller than a problem like navigating a robot around a warehouse, or heaven forbid, a self-driving car, where you have all these other cars on the road. And if I may be allowed to say this, you know, potentially idiots, humans who are driving in some of these other cars in ways that are unsafe and unpredictable. So the problem just really hasn't, the technique hasn't gotten good enough to scale. So I remember reading this Rebel paper. For a long time, they hadn't been able to get even techniques like AlphaGo to work for poker, because in Go, at least you don't know what move the other person's going to make, but once they've made the move, you can see it. Okay. In poker, you have multiple rounds of betting, but you still don't see their cards. And so it took a while before people were able to build up the math such that essentially you're holding a probability distribution of what cards you think your opponent is likely to have based on their particular behaviors, and carry this through multiple rounds. And ultimately, in the Rebel paper, they were able to build a computer that was superhuman. So basically, I do not recommend that you go online and play poker, because if you're playing against a bot, you're not going to win. All right. One last thing to discuss here is what they call actor-critic methods. So this is, again, terminology that you're going to see very, very often. I don't know if I can summarize this super quickly, but basically, in policy gradients, we said that we're going to have a differentiable policy. We're going to use a neural network. We're gonna update that kind of like gradient descent. In actor-critic models, you have both a Q-learning value function and a policy grading. So you're kind of combining the best of both worlds. That's really the gist here. Okay. And so ultimately, your loss, your update is going to be, here's how I'm going to update my policy, and then here's how I'm going to update my values. And in theory, what you can do is you can have one neural network with two prediction heads, and one of the prediction heads is the policy head, and the other one is the Q value head. And so then basically now you can imagine you're getting twice as many inputs. So you're getting, double the learning for your gradients for your neural network, and you can use the correlations from what you learn about high values, low values with how you decide what policies to take. They're obviously going to be very related, right? So then this one neural network gets to take advantage of both of those sort of input signals. And so that's the core idea. I'm not 100% sure who coined the actor critic terminology and why. I haven't personally found it to be intuitive, but maybe for somebody else it is. But basically it says here, the policy network predicts what you're going to do, what actions you're going to take. So then, okay, fine, that makes kind of sense that you would call this actor. And then the value network is termed the critic. And I mean, I don't know. Like I said, I could try to make something up as to why you should call it that, but I don't know that my intuition of what a critic is, like a movie critic, I don't know that kind of matches exactly what's happening here in these actor critic models. But if you find it intuitive, great. And if you don't, just remember that basically you're doing some version of value function learning and policy gradients combined. So I don't know, most of the stuff that I don't follow RL super closely. Most of the stuff that I've seen that's on the cutting edge is usually actor critic stuff these days. All right, and so that pretty much covers a whirlwind tour of core reinforcement learning. There's one other topic, which is offline RL. And offline RL historically has been very tricky because the idea is, let's say you're doing something and you don't have a simulator, okay? And let's say that something that you're doing is very dangerous or very expensive. So you can't afford to just put an untrained robot in there and have it do thousands and thousands of episodes and learn, okay? So what do? So one of the things you can do is you can get recordings of humans, of whatever, algorithms, heuristics, of them doing this task. And then you can show these recordings to some type of agent and try to get them to learn. Historically, this is very difficult because this is extreme off policy. So if you think, wow, there's 10 possible actions, and I bet it would be a good idea to do action 6. What if none of the recordings do action 6? How are you supposed to confirm this hypothesis you have that 6 is a good thing when all your recordings did either action 4 or action 9? It's like, well, so that's the real dilemma with offline reinforcement learning. And there was this really cool paper, I think it was about 2 years ago now, or whatever. This is the diagram for it. But this paper, this model that they called decision transformer. Basically, we see transformers doing long sequences in our LLMs. They said, well, I have these long sequences that are state, action, blah, 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 right? So what if I train a LLM-ish looking transformer model to do this? They were able to get it to work with one little tweak, and I thought that this tweak was really, really smart. I haven't seen a lot of papers. I don't really know what has come of this, but they said the disadvantage to offline RL is what I was saying. You can't really explore an avenue that you want to. You're forced to only explore the avenues from whatever other people have already done in these recordings. But these guys figured out there's an advantage, however, that you can parlay from offline RL, which is normally in the online setting, we get one reward at a time. And so like in TD, we're just using this single thing in order to update things. But when you're doing offline and you have a recording, you actually can accurately calculate the full return at any time step from there until the end. It's not the estimated value. Okay, the expected value. This is not the average, but this is the actual return you got from this and all future sequences. So, so what they did is, if you saw before, we had this thing where we write state action reward, blah 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 blah. They were clever and they substituted, instead of the reward, they plugged in the sum of all the future rewards, which is your true objective, not your, it's not, you don't care about the immediate reward, you care about the sum of the future. And so they said, let's show that to the transformer and let the transformer predict that, because that's actually what we want. And so I thought it was really cool that they basically said, like, it's kind of dumb for us to formulate the offline problem exactly the same as the online problem, because it isn't the same, and we actually now know the future. So when they changed it from the immediate reward to the long-term return, then they actually got the transformer to learn quite well. And so this decision transformer had, to my recollection, it had state-of-the-art results for offline RL. I haven't heard a lot since then. I don't follow RL that closely, but I haven't seen anything where people said, like, oh my God, this swapping of the formulation for offline RL has caused this massive breakthrough. Um, so, um, um, but that's certainly another area where, again, sometimes you don't have a simulator and sometimes you can't afford to do it. So you need to do this offline thing. So if you can build a simulator, great. There are, physics simulators, self-driving simulators, game simulators, blah, 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 blah. But if you can't build a simulator, then this is the next best thing. All right. So that's our whirlwind tour of RL. I was looking, it was actually almost exactly 3 years ago that we went and we covered a big chunk of the famous Sutton and Bartow Introduction to Reinforcement Learning book. Have here. This was the first session. It was May 15, 2021. So those videos are on our YouTube channel if you're interested in RL and want to look a little bit further into this. And then you can get a little bit deeper. I mean, we went very fast through all these concepts. You can get a little bit deeper appreciation for the techniques. There's blends between Monte Carlo and TD learning, and a lot of stuff on policy gradients. It's the most famous reinforcement learning textbook. It's a very good book for reason, and even better, Sutton does make the book freely available for download. So you're free to just grab a copy of it and look at it anytime you want. All right. So I think that's where we'll end things for the book club for today. Again, next week we're going to finish the book. So there's 2 chapters left. They're not super technical, and so we've done it. Next week we'll be finishing out the book. Any last questions on reinforcement learning before we wrap up here?
I was going to add just a tiny bit of extra flavor text to the question earlier about why isn't RL like taking off like everything else.
Please.
Um, my there's kind of 2 critical problems that I see with the RL stuff. One of them is that there's a lot of problems with the sim to real simulation to reality. So like we have all of these things where we can simulate some environment and then we train a model on it and then we take it to reality, and like the tiniest friction coefficient is different in the real world than in the simulated robot world. And then the entire thing just breaks down. Your simulation couldn't carry over. That's a very common problem that people end up running into. So you need something that you can quickly simulate or do in reality very fast, but there's very limited things that you can do in the real world. Like if even if you're doing like, I want this robot to learn how to stack 3 blocks, consecutively, just the process of like the arm needs to move and set the blocks three on top of each other. Like you're limited by the physical like speed of the movement of the arm and everything. So if you want to train something RL in reality, like it just it cannot learn fast enough in most scenarios. We're getting much better at that stuff, but it's still to the point where not really realistic. And then the other thing is just the compute quantity is like the floor for even getting something decent is quite high. So like even the cart pull problem and other stuff like that. Um, I went and I played with a lot of the toy problems, and it's like even for the most basic of problems, it's still going to take me 8 hours of training for it to even start learning anything at all. So if you're going at a real problem like DeepMind and OpenAI have, like the actual compute that you have to throw at it and the number of iterations is massive. And so most people can't even take a stab at those things because they just don't have the compute available to even it's a bit of a gamble on some of these things. Is it going to work out or is it not? We don't have the priors on it. So if you're going after it, you have to commit heavily. Those are
Thanks,
those are my
Ryan.
two things. Yeah.
Yeah, those are great points. On the first point, I remember I was looking at some paper. I don't remember at all which paper it was. Um, but they had trained this robot to take a scoop of tomato sauce and spread it around on the pizza dough. Um, and what was really cool about this particular model is that you could actually nudge the pizza while it was doing it, and it wouldn't completely mess up. It would actually like see the pizza moved, and it would actually, right. And so it's like if you think about this, right, like this is something you could teach a 6-year-old. Like if I move the pizza a little bit, you don't just spread it around where the pizza used to be. You have to actually follow where the pizza is, right? Um, and then I was thinking about remember there was that Kaggle competition. It was this multiplayer
Yeah.
game,
Yeah.
and so the uh, it was intended to be like a reinforcement learning kind of a thing because it was this slightly more complicated multiplayer game, the halite stuff,
Yeah.
whatever. Uh, and I what I recall is that the person who won that competition did not use reinforcement learning. They had some heuristics and algorithms, and that was so it goes to show like how minimally valuable using RL is.
Yeah. I posted the link to the highlight. That was one of the ones that I took a stab at and I just couldn't after all of our reading on the reinforcement learning stuff, I couldn't really make any significant progress, and most of the solutions ended up being people's kind of handcrafted bots rather than
Yeah,
any reinforcement learning. Yeah.
yeah. I remember Lux on Kaggle too, but I don't remember if people were able to actually use RL for that one. So, and there were people that used RL for Halide, so it wasn't
Yeah.
impossible. Some people got it to work, but they didn't, and they did okay. They just didn't win the
Yeah.
competition. So, all right, cool. I'm gonna end the recording here as soon as I can find the darn button.